All right. Hello, everybody. This is Christiana from the Coiled team, and I'm so excited to welcome you all to tonight's Coiled webinar, The State of Distributed Computing. And we're going to be joined by Peter Wang and Matthew Rocklin. We're going to get started in just a second. I will be introducing Matt and Peter, but first we'll let everybody get settled. As you join, let us know where you're calling in from in the chat. And yeah, we'll kick it off pretty soon. But yeah, let us know where you're calling in from. So excited to have you. Hey y'all, Christiana from the Coiled team here. So awesome to have you for tonight's webinar, The State of Distributed Computing. It's amazing to see so many folks joining from so many different places here in the States and across the world. So thank you so much for being here. We're going to get started pretty soon. We'll give folks a few more minutes to join in. So in the meantime, if you haven't already, do let us know where you're calling in from in the chat. Let us know what you're working on, anything, and get settled because it's going to be an awesome conversation with Peter Wang and Matthew Rocklin. So we'll get started in just a few minutes. All right. Hi, everybody. I'm Christiana. I'm from the Coiled team, and I'm very excited to welcome you all to tonight's Coiled webinar, The State of Distributed Computing. If you're just joining, we've been asking folks as they settle in to let us know where they're calling in from or a few words about what they're working on in the chat. We'd love to hear it. And as Matt pointed out, when you're doing that, make sure you send that to everyone and not just the hosts and the panelists. But welcome. We have a very exciting discussion coming up with Peter Wang, co-founder and CEO of Anaconda, and Matthew Rocklin, CEO of Coiled and the initial author of Dask. I'm going to pass it over to Peter and Matt pretty soon, but first it is my pleasure to tell you a little bit more about them. Let's start off with Peter. So Peter has been developing commercial scientific computing and visualization software for over 20 years. He has extensive experience in software design and development across a broad range of areas. Peter's interests in the fundamentals of vector computing and interactive visualization led him to co-found Anaconda. As a creator of the PyData community and conferences, he devotes time and energy to growing the Python data science community and advocating and teaching Python at conferences around the world. That's Peter. And now for Matt. Matthew is an open source software developer in the numeric Python ecosystem. He maintains several PyData libraries, but today focuses mostly on the Dask library for scalable computing. Matthew worked for Anaconda for several years, then built out the Dask team at NVIDIA for Rapids, and most recently founded Coiled to improve Python scalability with Dask for large organizations. Matthew has given talks at a variety of technical, academic, and industry conferences. So without further ado, I will pass it over to Peter and Matt for tonight's webinar, The State of Distributed Computing. And as we hear from Peter and Matt, feel free to ask questions in the chat or using the Q&A feature. Buckle in and have fun. I'm pretty excited. So without further ado, Peter and Matt, take it away.
Thanks, Christiana.
Thank you, Christiana. Thank you for having me here, Matt.
Happy to listen to you anytime, Peter.
Well, and same. So I have a few slides here that I thought we could maybe kick off with, and just a level set and provide some context around my thoughts around this topic. And let me see, I'll go here and share screen. Okay, how's that look?
Beautiful as always.
Okay, great. So these are just a few slides. It shouldn't take very long, but I thought it would be really useful for us to motivate the discussion a little bit. And these are just kind of my observations and sort of high-level thoughts on what I've seen of distributed computing and how it intersects with Python. So I think the common way people think of distributed computing is they tend to think of like lots of computers, disconnected or connected via networks, but they're trying to get a lot of computers or a lot of processes talking to each other. And so there's sort of this distributed across space concept. But one of those powerful concepts I learned relative to distributed computing is to actually kind of do a Fourier transform of that and think about distributed computing, most of the challenges as challenges in time, whether it's synchronicity, whether it's atomicity, whatever kinds of things. Most of the problems in distributed computing are not actually intrinsic to the topological layout, but to the temporal aspect of when data shows up where it's supposed to, when something else is expecting it. So I think when we think about distributed computing, it's useful to not just think of that spatial aspect, but the temporal aspect. And then lastly, here in the PyData world, as we think about where Python is intersecting business use cases, it becomes extremely important to also consider the aspect of data. And what I mean by that is that the boundaries of data semantics, the boundaries of who owns which data system, those things are actually even harder barriers than any physical or computational boundary, because those oftentimes hit political boundaries within organizations, right? Governance or just sort of like other kinds of political concerns. So it's important. Sometimes this gets ignored, but when we think about why we use a distributed system versus just running a shell script on a single machine, these are all reasons that motivate that. So let's give an example of what I mean by that. So for instance, if you say, oh, my data is bigger than memory, like pandas blew up or whatever, that then you can think of that as mostly a problem of space, right? So what you want to do is use distributed computing primitives to synthetically create a bigger computer out of lots of smaller ones. The time problems you run into or synchronicity, atomicity problems, generally, if you're just doing this for yourself, these can sometimes be treated naively. It may not be the most optimal thing, but it's also not necessarily an impossible problem to solve. And because this is really for you, like when you're doing data science exploration, this is, there's really not a data governance issue or any potential that one part of the system thinks a particular row means something different than another part of the system. Because you're sort of taking a more uniform approach to sort of federating the work across a lot of similar systems. But let's look at something else, which is, let's say you're building an ML pipeline. And in certain situations, a model will take a lot longer to train if certain inputs are a particular way. And what you have then is a application that's pumping data through, and different parts of that pipeline or part of that application, different parts have different scaling, latency characteristics depending on input values or depending on other kinds of factors. So this is now actually a time problem, not so much a, how do I talk to different computers and make that less annoying. This is more about how do I make sure when I do have to scale to a large number of computers or bring them down, that I can still hit certain latency and certain SLA requirements. So this is you see this in ML pipelines a lot. This is not as much of an issue when you're doing data exploration, right? And then a third simple example of the data boundaries is when we have to build streaming systems that are taking data out of one system, putting them into another. Maybe you're taking data exhaust out of an application and you're putting it into some other database, or you're transforming some master database into certain kinds of downstream analytical data stores. So in these cases, you want to build a data streaming application. It's certainly a distributed application, but your motivations are because these different data systems are governed by different requirements. They have different kinds of users. And oftentimes, more often than not, they have very different governance applied to the data. And then sometimes there's differences in data semantics. So you're building this distributed system, you have to think about, how do I represent and faithfully transform those kinds of semantics and rules from one system to another. It's not just a issue of, can I make a machine respond in time, or can I marshal enough machines or be resilient to failure? So I would say this use case is the farthest from the data exploration use cases, even though when we're doing data exploration, we are oftentimes using Python to extract data out of one place into some local place so we can play with it. In this particular case, I mean that when we're putting actual running robust data pipelines in place. So I would also say this has traditionally not been in Python's wheelhouse. This has been what traditional data warehousing and enterprise data warehouse technologies are used for. ETL technologies, or nowadays you'll find ELT more often. But it's not just that Python isn't usually found in this. I think a really important thing to be aware of is that Python is usually the glue or duct tape or sort of like shadow IT tool that's brought out when these systems fail to meet the needs of the different parties involved. So Python is almost like the anti-hero in these situations. And so a lot of the tools, and this is something we're going to keep kind of coming back to, because this is where you find SQL. This is the land of SQL, right? And a lot of the tools that we have in the Python data ecosystem, they're sort of native CSV. They can talk to SQL, but then to actually grow up into, turning into bulletproof SQL-based first-class citizens, I guess, in SQL land, this is the thing that we have to think about. Is this where the future of distributed computing in Python is invariably going? So anyway, that's kind of those three things. Any questions or comments on that, Matt?
Yeah, so like you usually speak at like a high level. I'm gonna have my brain running pretty fast trying to catch up, Peter.
Mm-hmm.
So if I can, I just want to I want to dumb it down a little bit. Can I ask you to walk back actually to, I think this idea, you have space, time, and
Sure.
politics, lack of a better word. just to sort of say this again to you, what I'm hearing from you say is that I either want distributed computing because I've got a problem that's so big I couldn't possibly solve it in one machine. So I need like a meta machine. That makes sense. I think we're kind of used to that. Or I need this thing to run faster. I'm running some analysis and it takes a week to run. I need to run that every day. And like, I actually need that result faster in time. So I want to accelerate something. Maybe I could run it in this fixed amount of time. I want to run it in a faster time for business reasons. And the third piece actually, in my mind, doesn't seem like a reason for big data. It actually seems like more of a trip mine that big data systems trigger. So, when I have to use these big machines, suddenly I've got to use infrastructure inside an organization. And now I've suddenly got to bring in 3 other groups to sort of sign off on my computation. And so now I'm like in this the harder level of the video game that I'm playing.
Right.
Am I summarizing this correctly?
It's close. I would say the point of this slide, I should maybe put motivations for distributed computing, right?
Mm-hmm.
And by time, it's not about accelerating your time to result. It's more that there's one business requirement or one computational need over here. it's operating on a particular kind of time frame. Let's say it's a transactional business data system, or it's an event stream, right? And then there's another system over here that has a different set of temporal requirements. And so we have to build something that couples these two things with different temporal requirements and stuff. And that is a distributed system. It may only have two computers, but it may be way more complicated than a giant 1,000-node supercomputer for reasons that have nothing to do with how many nodes, how many running, operating systems are holding processes live, but rather what correctness means and how to account for errors and how to meet the requirements of both parties that have these requirements on these two machines.
So when I think distributed systems, I think of a lot of computers that are temporarily tied together to serve some need. And that's actually, you're taking a broader definition.
I'm taking a much broader definition of why. So my thing goes back to, we have a distributed system when we can't just run a single linear shell script, right? Why can't it just be a shell script? Like, if I'm just kind of being like the most sort of stubborn old crotchety person possible, why can't we just write a shell script? Well, in this
case we could, right? We could write a shell script and it would pull data from one database and it would shove it into a different database. But there's still a distributed system. There's the first database, the second database, and the machine running our shell script. If you're saying that is a distributed system.
Yes, and most importantly, the requirements about correctness, when you will get paged at 3 a.m. because your shell script stopped working, or when someone will yell at you because your shell script like DOS to their database, whatever it is. This is what I mean by the time, that the reason why there are multiple databases that you'll find these in business environments is precisely because they actually have different business requirements around uptime, around latency, around who can see what data. And that last point kind of ties into the data part. And maybe now you see what I mean by this slide, that sometimes the motivations for having different computers, why you can't have a single script, is because literally those two pieces of data cannot appear on the same machine. You have to have something that extracts from one machine, something that extracts another thing from another machine, and then brings together in some Switzerland place, right? So that's another reason why we have multiple machines, and it can't just be a single shell script running in a single box.
Sure. Or like the Snowflake database has slightly different permissions around it than the CSV dump file that I put on.
Right, exactly.
Yeah. And that gets kind of to your point later on, you talk about Python as the glue language. Historically, we are that kind of hacky language that gets around all these barriers, probably inappropriately, and starts doing computation.
Well, appropriate's very judgmental and normative. I would say if it helps the business succeed as an overall big Gaussian integration, then we're probably helping people. Whether or not they have impedance mismatches in their internal governance of IT and what the users want, that's a different issue. That's an internal issue.
I think we're helping people with some risk, right? Which is usually appropriate.
Well, there's always trade-offs in engineering, right?
Yeah. Thank you for going back in time. I appreciate it.
Yeah. Does that make sense? I mean, do you see kind of where I was coming from with that? Like in terms of thinking about the motivations, right? For why we have.
I see like 80% of where you're coming from. I think I never fully understand you, Peter. Also, just for context for the audience, I used to report to Peter when I was at Anaconda. We've worked together for a long time. And Peter has tons of great ideas. It was always my job to try to understand what he was saying and try to turn that into code, which worked out pretty well. So this is the kind of conversation we often have. Peter just dumps huge velocity of ideas and I try to interpret it.
And it's worked out well. So
yes. No,
good.
Fantastic relationship. But yeah, please.
Yeah, well, I just had one more slide, which is looking at where Python distributed computing is today and taking a very sort of like MBA school approach to it. Let's build a SWOT diagram, right? And or a SWOT table, if you will. Strengths, weaknesses, opportunities, and threats. And I'm going to avoid reading the slide. I'm pretty sure people on the call here can read the slide. But I think kind of zooming up a little bit from here, the biggest thing that I see that challenges us is we have been really good at a worse is better approach. Like we are the tool you pick up and use, like you're just saying, the glue that ties a lot of these things together. And should we be better glue? Should we continue to be worse is better, jack of all trades, Swiss Army knife? Or now that we're finding ourselves and our tools creeping into business mission critical things, whether it's new applications in the machine learning, inference pipeline space, or whether it's displacing older things, displacing like SAS or other kinds of SQL sort of workloads. In those cases, should we think about what it means for Python to sort of put on a suit, right, and actually get better at better? So as worse is better, disruption from below, classic innovator's dilemma, or should Python distribute computing and the ecosystem here, should our vision be to, now that we've gotten into these business use cases that are so important, we really should focus on really knocking those out of the park and doing those really well. So that's, I think, a question that I don't have an answer to, but I think is the overarching question for us right now.
I really like that imagery of should Python put on a suit? I think that's actually a really interesting question. Do we want to wear a suit? Should we put on a suit? If we put on a suit, we can be more effective. It also changes our culture a little bit. Can we actually wear a suit? Like, are there Python shaped suits? We kind of need to like visit a fancy tailor and figure out, however Pythons fit into suits. Yeah, so I think, so I'm going to take over for a second. And I think that distributed computing, I think this is sort of shifting from a state of distributed computing to like state of Python in business conversation a little bit.
A little bit.
But I think that distributed computing, from my perspective, is actually a common case where that comes up, because everyone in the world has adopted Anaconda, and they never had to get any clearance from their IT department to adopt Anaconda. Right. Everyone just did it because it was the right choice. When you start getting distributed computing questions, suddenly there's IT departments and there's management. There's a bigger organizational involvement in making that decision, right? So I think folks who adopt Dask, they adopt on a laptop very happily. Some folks can do some sort of skunkworks project and kind of get something up and running for one or two people, and they're usually pretty productive. Then when they try to share that to the rest of the organization, that's when like the business units get involved, and so that's when they start sort of looking around for someone with a suit. And so that's, I think, an interesting question. So we run into this a lot at Coiled about, can we beat Spark at certain things? Can we play nicely with Cassandra or with Snowflake? Like, are we something that is Python and is Dask and is PyData more broadly something that the business can depend on longer term? And we kind of have to make some decisions. Do we focus on building up that dependability? Because that requires effort. There are lots of holes in the PyData space for that dependability. Or do we keep, to your point, do we keep doing worse is better? Do we keep focusing on new, more advanced applications, new exciting techniques? Where do we focus our energies? And that's, I think, a question that is a genuinely open question inside of Coiled. I suspect it's also an open question inside of Anaconda. Yep. What's Anaconda doing, Peter? Are you guys putting on a suit? Or are you guys?
We have a little bit. I think kind of to your question, I think the thing we have to be aware of is to have a robust go-to-market for those kinds of use cases it's not merely a product feature question, right? It is actually an overall go-to-market question. So your customer that's buying needs to buy a lot of things besides just features. They want to buy assurance. They want to buy, support's the wrong question. They want to buy peace of mind that this super critical part of their data architecture isn't just being given to a bunch of open source nerds, to put it bluntly. So I think when we talk about putting on a suit, it's not merely a matter of putting on suit-like features. It's actually a matter of organizing the community, organizing the commercial players in the community to actually be able to go to market for those kinds of use cases. And you're right in that it does have an impact on culture, but not more importantly, but there's almost the question of like, are we even the right people to be doing that kind of thing? Okay, what I mean by that is if you look at other foundations around commercial open source, like the Linux Foundation or Apache, they have been doing this kind of go-to-market activity to the top-down technology buyer. They've been doing that for a very long time, and they've been quite successful with it. And maybe their stuff doesn't stick around very long. Maybe it churns out every few years, but it's a thing they're good at doing. From the Python land, we've always been this grassroots kind of thing. We start with the practitioner. We build what's good with the practitioner, what they love. There's a joy aspect there. And I'll tell you, the top-down CIO selling, there's no joy in it at all. Okay, so if you want, and that's just, you can quote me on that if you want to, but the point of it is, but they know it too. Like nobody pretends like it's that, right? It's a whole lot of, Gartner and all these other kind of people. And so what I think back to is maybe it's not an imperfect example, but the Apple Lisa, where they started with the Apple II, which was fun, accessible, affordable, had all these different things you could do with it. They went and tried to build the Lisa, which was like boom, like this. It was an amazing machine, but really expensive. It kind of overshot the mark. And fortunately, they did a quick save with the Macintosh, and that kind of then was their next gen machine. But I want to make sure that the overall, PyData ecosystem doesn't rush so hard at this possible opportunity that it goes so hard, puts on a suit, and it shows up at the table, and it's still seated at the very end of the table, downstream of the SQL, traditional data warehouse stuff, all of the big cloud hyperscaler native offerings, then downstream from Hadoop, downstream from Spark, then finally down here you've got Python in a suit, like an orphan with a bowl asking for a little bit of gruel, and that's like no good. Why go through all the trouble to put on a suit just to get that, right?
I mean, going back to your slides for a second, you've got a set of strengths and opportunities here. And so in the chat, Jonathan Moore points out that, I'm going to quote here for a moment, the IT departments who wanted to kill Python for Spark and Hadoop in 2015 have changed their tune now that ML has replaced big data as the promotion generator.
Yep.
And so it seems like the growth of machine learning has catapulted Python to the front of that table a little bit right now.
Yeah, it's true.
So, I mean, maybe ask a question like how has the business landscape changed, especially on distributed computing, in the last few years, and how does that affect how community leaders like yourself think about how to position Python and PyData in this landscape?
Well, let me answer that question with a question. You think about what are the things.
As all good business leaders should, Peter.
Yeah, I've learned a couple of tricks. What are the practitioner tools that led to machine learning becoming this buzz thing that everyone talks about? Scikit-learn, pandas, NumPy, SciPy, the standard stack that we know. Dask, okay, I should mention Dask a lot. But all these tools are practitioners use. And when a C-suite tech executive goes to make personal decisions around ML pipelines, infrastructure, and things like that, all of the cloud hyperscalers, all of these startups that have been funded with VC funding to the tunes of hundreds of millions of dollars, selling proprietary or whatever kinds of solutions, they capture all of that revenue. 0%, rounding to a few digits here, 0% goes to the tools that actually put Python on the map. 99.9999% goes to these other kinds of things that say, oh, this is how you do Python machine learning pipelines. This is how you do ML ops. You buy this thing, you turn on this thing in this cloud provider, right? I'm saying this in a descriptive way to paint what a failure of go-to-market looks like, right? So if we go and say, hey, Dask is great, people love it. You have this chat, and I'm looking at the chat, and it warms my heart to see how many people love using this stuff. And the question is, if we're going to take Dask and sort of, let's say, Python next-gen distributed computing as a technology to go to market with a top-down kind of thing, we don't want to lose that game to superior messaging and superior kind of hyping from these other vendors, right? And that, do you see what I'm saying there? Like, that wasn't really a question, but that was a.
Yeah. So I think what's nice. So from Coiled's perspective, from a Dask perspective, there's a pretty clear business model, which we steal admittedly from Databricks, which is a usage-based business model.
Sure.
So more people that use Dask, the more money we make if they're using it through us on the cloud. And as a result, like we're kind of in the middle of all of that usage. And so now if someone, let's say Prefect, built on top of Dask and sells their thing, we get some fraction of that revenue. And so there's actually a very nice sort of taxation system that's set up. It's actually quite convenient for distributed computing systems, which I think makes them.
Yeah, it's true. It's true.
Yeah. Right. My condolences for Anaconda. It's harder to monetize a package manager.
It is.
But I think that puts distributed computing, again, distributed computing was interesting in a business context because it forced us to talk to IT departments. It forced us to talk to business units.
That's right.
Distributed computing sort of forces conversations aside from the main practitioner. And again, Anaconda was super successful at convincing practitioners that they were the right technology. At Coiled, at Dask, we have this extra challenge of having to convince IT people, and that's actually sort of a benefit because it forces them into a conversation, forces them to acknowledge us. We still have this question though of can we put on the suit? And I think that it's actually been really interesting as we've made it easier and easier for people to scale up to larger and larger workloads, we've actually found that the entire PyData space has all these interesting words. Like it's simple things like reading or writing to Parquet files is really easy below about a terabyte. Above about a terabyte, a variety of things break, right? So Dask breaks, but Arrow also kind of breaks, and Thrift breaks. Like a lot of the things that we are depending on are not built to operate at the sort of like 10, 100 terabyte scale. And so I think there's some interesting questions in Python of whether or not we want to go after that sort of suit wearing class of problems. And I've shared a blog post that I've sent to you. I think we'll probably publish it sometime next week. Where we just go through all of the challenges of trying to actually compete against Spark at that sort of 100 terabyte scale. And there's a bunch of stuff. And it's interesting because it's not just Dask. A lot of things are Dask's fault, but it kind of requires all of us to collaborate. And so I think if I were to ask the question, it's that, can we put on a suit? Sure. I think you and I were both wearing, nice button down shirts, not necessarily suit material. I'll button my top button to match you, actually. But can we put on suits and still operate as a community? Because as we're trying to work on these problems, it actually requires, like, I know we've been working with folks at Anaconda who are doing some of this work, folks at Voltron who are doing some of this work, folks at NVIDIA who are doing some of this work. We have to sort of both put on suits and continue to operate as our sort of hippie commune community gathering. So can we have I'm now thinking of like a cooperative table full of hippies who are all wearing suits. This is actually maybe even more laughable than the Pythons wearing suits.
Well, I mean, cooperatives can be, quite successful commercially, right? And the consortium model is quite common in any industry. So I think it's very possible for us to form a collaboration, a commercial collaboration and consortium among the now several companies working, in the PyData space. In fact, I think it's not just possible, but I think it's actually imperative that we do that. But that aside, the question of, for Coiled, and this is your decision, obviously, if you have customers who are desperate for you to go and tackle the 1 to 100 terabyte problems, then you should, in general in business, you should listen to your customers and follow them. But one thing I would say is thinking about where the puck is going, not merely where it's coming from, and where there seems to be a lot of pucks. We think about where the puck is going, and a little bit to Jonathan's point about ML pipelines now driving a lot of IT requirements. I would say instead of going after the data lake, maybe render onto, saying render onto Caesar. What if we render onto SQL what is SQLs? Let the data lake, the giant data lakes as they're getting bigger and bigger, be somewhat in the domain of specialized tools for handling robust distributed compute on those massive sizes. Again, with SQL being a native language, and we'll have better and better SQL bridges. But what about what's in the middle? Let's call them data ponds, okay? And so if we think about that, the reason I bring that up is because this is going to be a little bit of an aside, but it's a really important thing for us to think about as a community. My expectation is that we will continue to be good enough at shadow data management to be around for a long time. Okay, so that means that if the PyData stack, mini data on a flock of like Raspberry Pis is what's going to kind of be your data warehouse for a little bit. All these things, we're just easy to get into these places. If that's going to continue to be the case, what I completely expect to see is that once these ML systems start feeding back into the prediction and training infrastructure in a closed loop way, then the point where the data comes back, where the observational data comes back and hits the training processes, at those junctures, you're going to now form a place where data will pool. Traditionally, data pooled in places, and again, data has gravity, right? As our friend Andy Terrell loved to remind us all, data has gravity. Traditionally, data gravity was these giant data warehouses for historical legacy reasons. But now, once we start putting lightweight inference infrastructure out there, once we start having storage be so cheap, once all these things start happening, we're going to see data pooling into these little ponds in all these places. And you're going to want to govern them. You're going to want to transform data between them. You're going to hook them up and actually do all sorts of data transformations. What if Python was excellent at that emerging thing?
Right. So I I mean, maybe what we're getting to is what is the scope of distributed computing in Python? Let me try to paint a broad picture for a second. So you've mentioned there's things like SQL databases, which are excellent at doing SQL stuff. There are things like distributed deep learning, like Horovod. There's things in the middle. There's sort of Spark, there's Dask, there's Ray, there's all these sort of tools in the middle. Where should Python play? Should we try to be really aggressive? And should we try to own everything? Should we sort of stay where we've been historically? And should we just think about those sort of interstitial glue functions? How ambitious should we be? And as we're being ambitious, where should we target? Should we target the ETL? Should we target SQL? Should we target general ad hoc computing? Should we target machine learning? Should we target very advanced machine learning? And I think, Spark kind of focused over here, Ray kind of focused over here, Dask was kind of in the middle somewhere. And the question is, something I have to answer in Coiled is like, where do we focus in the future? Can we do everything? Is that in scope? In the Q&A, Anar asks, and actually I'm going to blend a couple of questions here. I'm going to blend a question from Anar and from Adolphe Trudeau, who are asking, like, is it actually possible for things to become entirely transparent, so that things just work well in an HPC environment, and we don't have to care anymore? And so that's again like an ambition, right? Are there data structures that are protocols that we can build that would make this dream a reality? And knowing you, I think the answer is yes. Let's build all those protocols. But maybe you're always a pretty ambitious person. What you're also saying now is, well, maybe we should be focusing a little bit on those glue cases. Maybe we actually can't own everything. And so again, maybe I'm going to summarize what I said. Like, what is the scope of distributed computing in Python over the next 5 years, let's say? Are we going to own everything? Are we going to stay to certain areas? If so, which areas should we focus on? And how can we achieve this?
Okay. I have a lot to say on this. So
I know.
I think we should be thinking about, well, and this kind of goes back to the very first slide on there are use cases where Python is brought in to try to solve a distributed computing in terms of many machines, the sort of use case. And there's use cases where it is primarily motivated on the data system side. So trying to create an HPC environment where you have seamless bursting and scaling, I would say that's more in that in the compute orchestration aspect. And I think that's an area where we will see a co-evolution of the Python distributed tools as well as the algorithms. And you actually already see this in deep learning and ML a little bit, where between the hardware topology, the software orchestration layer, and then the algorithms, these sort of all co-evolve to solve for most performance, most cheaply, with a minimum of pain. So that's going to continue to be sort of some iterated gradient descent, pardon the pun, into some optimal. And I think that will probably be a natural evolution there is probably the best thing. Because I think if we come out and say, well, here is the end all be all seamless burst framework for Python computing HPC, we actually will be doing the wrong thing. I think we should be doing iterated, working with the kinds of algorithms and users there. Does that make sense?
Sure. It does make sense. I think you're answering the question from the perspective of a business owner. I want you to actually take a step back and put on your sort of community management hat.
Oh,
so not necessarily from an Anaconda or a Coiled perspective, or from a Python perspective. In 5 years, will Python just be the language that everyone does all of their computing in at scale?
To make that really happen, okay, go ahead.
Or will we still be balkanized? Will Spark still be around? Will databases be around? Will we be handling just the data ponds and the interstitial spaces, or will we be handling everything?
This is another part of the answer I have for you, is that 50% of Spark is Python. So Spark being around doesn't mean Python isn't in these places. And in fact, Databricks, the Spark company, is looking at alternative compute infrastructures to tie to Python inside the Databricks notebook, right? So it's not even Spark at that point. So, I mean,
I think when we say Spark, when you and I say Python, though, I think we mean the set of libraries that are built around Python and have a certain sort of usability and ethos around them. Spark has always been sort of an ecosystem unto itself, whether it's written in Scala or C++. Like you can't use the rich ecosystem that has been built around Anaconda and PyData
Right.
over the last couple of decades.
Right.
Even if you can call it from Python, I feel like that's a different system.
Fair. I think those systems aren't going to go away, and wherever Python is able to get usage, they will build adapters into and connect with those things. I think there's no way over the next 5 years, there's no way that Python will significantly displace SQL or anything like that. There's a lot of data pipelines that are currently in Spark that may move over, but maybe not. What I think, I mean, from a community orchestration grandmaster perspective, from a realistic standpoint, we don't have the resources to go after everything all at once. So our constraints then should be, what are the areas that we should have certain focused efforts on that maximize our optionality as an ecosystem? And so I think, number one, go after the parts that are most likely to have a lot of upside that people are not going to be able to take away from us. That's why I bring up the data pond thing. Like, make it really simple. This is why I continue to support the development of intake and lightweight data catalogs and all these kinds of things. This is still an area where, let's just look at the past. Python has been great at practitioner-driven worse is better. So let's keep focusing on the worse is better bleeding edge there. But in the meantime, if there are people who can marshal some energy to make a strong focused effort into particular other areas which may be tougher for the ecosystem, for the organic adoption to go into, to do better is better, then they should do that. So in a sense, what I'm telling you is maybe the ecosystem shouldn't do this, but Coiled should do this, right?
Yeah, I was about to say, I think it's one of the cases where I'm more ambitious than you are, Peter, which is very rare in our relationship. You're usually a visionary.
I just want you to think that. It's useful for me, for you to think that. No, but it is the case that I think you, with Coiled, building a product for the 1 to 100 terabyte use cases may be an absolutely an awesome thing to be doing, right?
Well, to be clear, I mean, lots of Coiled users are on the sort of 50 gigabyte use cases. We care about all sorts of folks.
Sure.
But as we get to higher and higher use cases, we just hit more problems. My usual analogy here is that building Dask or any distributed system is kind of building a race car. You can't build it in a garage. You got to build it on the racetrack. And you drive it around the racetrack and things break. And as things break, you have to fix them. And you go to 50 miles an hour to 100 miles an hour, 200 miles an hour. And when you're at 500 miles an hour, aerodynamics becomes a big issue. Or if that little small nut on the engine was loose, it flies off and kills the driver. Right. And so, but as we keep doing this, we keep driving faster and faster, and the race car still runs just fine at 50 miles an hour. But I think what I'm seeing is actually a huge appetite of folks who want to go to much bigger scale. They want to get off of Spark. There's a huge urge to drop Spark at these stages. There's also a huge urge at the exact same time to get more into more general purpose computing, right? And so I think that in Dask, we've always flipped between these two things. We first built it to go after sort of the pandas NumPy use case. And about half of our users just wanted the sort of internal engine of Dask to do some completely bespoke general purpose parallelism. And so we've always sort of been able to blend between those two things. But I think that gives us the ability both to go after these sort of older use cases and to to claim and to really support this whole new sort of ecosystem of newer use cases, machine learning, but also just sort of general purpose systems engineering, where I think we see Dask being used a lot today. Right.
Well, I mean, on the general purpose computing or general purpose distributed computing thing, I am not a particular expert in that area, but from what I can tell, there will always be, as long as you have two computers on the planet, there will be people interested in distributed computing and building and networking them together, making a Beowulf cluster, right, or something like that. So in the general purpose computing, I think the architecture of Dask is nice in that it lends itself to people doing these kinds of things. But in terms of a community, well, I shouldn't say community investment, but in terms of a business case perspective, right? What do you think are the fundamental drivers that will, ensure a longevity of that demand, or gives you hope for success, long-term success for Dask in that area, and it's not simply an interesting toy, thing to do right now.
Sure. Yes, maybe what I'm hearing you say is that the Spark case seems to be more profitable, so it makes sense to go after.
Mhm.
But at the same time, I think that by not going after Spark historically, Dask has historically done all of the other stuff around Spark. We've
Mm.
actually created a lot of new domains, a lot of new capabilities. We've unlocked a lot of markets.
Yeah.
So I mean, so a good example there is, like all of the X-ray users, people who are in
Mhm.
geosciences, who are in satellite imagery, who are in energy. Like Dask is really the only game in town for that set of folks, or that shape of data. Similarly, technologies like Prefect or workflow management tools, which look nothing like big data tooling. That whole market was created, not created, but that whole market was accelerated by capabilities like Dask through this sort of very general purpose parallel computing. And actually, a decent chunk of our customers came from Prefect. They're actually a wonderful partner of ours because a lot of their users want to deploy Dask. And so I think that while the big data world of Spark and Hadoop was able to really create this large market around business analytics, there were all these other latent markets that weren't created. And I think technologies like Dask were able to unlock a lot of those markets. So I think that's actually maybe it's an unknown opportunity. We don't know how many new frontiers there are to go unlock.
Mhm.
And so it's an unknown, which it was exciting. It's not the
That's
clear,
true.
it's
Yeah.
not the clear business use case. But as we've gone through that, we've found very clear business use cases. I think X-Array, Rapids, Prefect, these are all examples of that.
Well, and
Advanced
Rapids is a
machine
good
learning,
example. GPUs are obviously the first thing that come to mind when we talk about heterogeneous hardware, but they're not the last by any means. It's the first chapter of a very long journey that everyone's going to be going through, right? So if you have a compute infrastructure, a generic distributed computing infrastructure that you could use across heterogeneous hardware, and if you need to go then, optimizing even further down, you have tools like Numba and JAX and other kinds of things that can take you even lower. Those are the kinds, that combination is incredibly powerful, right? So our ecosystem has a lot of, I think, great potential in that area.
Yeah, and this is one of the cases where I think even though we're not as mature as Spark on some of these cases around stability or other things, we have this battering ram of hardware that we have access to because we're Python native or we're on native architectures.
Right.
So I think like NVIDIA, the NVIDIA Rapids team where I used to work, we ran a benchmark, the TPC XBB benchmark.
Yep.
And I think this is a benchmark of.
Yeah, go ahead.
This is like a benchmark for like general data science use cases. I think they're like mimicking some retail store or some bank or something. It's a pretty common use case. And various companies were competing usually with Spark or Hadoop to get 10% above each other with different kinds of hardware configurations. And NVIDIA with collaborators like Coiled and Blazing at the time, we were able to get like a 20x speed up and like a 7x cost of ownership reduction on that. And so we're able to just like destroy a previous generation of architecture, which is really exciting to lots of our large companies. Companies see those benchmark numbers and they get very excited, reasonably so.
Right.
But what I think is interesting and what's very challenging, I think you might appreciate, is that GPUs are really just the first part of that story about accelerated hardware. So most people are excited about GPUs because of deep learning, and it's a very easy thing to accelerate deep learning with GPUs. Throw a GPU in there, run TensorFlow code or PyTorch code, it gets 100x faster. But when you're doing more data intensive computing, which is usually about 100x the cost in an organization in machine learning training, when you're doing more data intensive processing, you actually have to care a lot more about data movement and about data storage and access.
Yes.
And that's a much more balanced thing against computing. And so GPUs can make your computation really, really fast. But now if you want to get the whole system to be fast, you need to start thinking about really fast networking, hence why NVIDIA purchased Mellanox, the InfiniBand hardware company.
Right.
You have to think a lot about really fast storage using technologies like Pure. You have to start thinking about the CPU to GPU to disk interface, hence the ARM acquisition, right? Like there's all these sorts of things that's much more balanced distributed computing infrastructure, which are quite challenging to get right. Anyway, you're talking about GPUs and going beyond, and I think this is the beyond, or one aspect of the beyond.
Yeah, no, I guess I initially, when you bring up the general purpose computing thing, it's sort of maybe what we're converging on is the idea that, and we could have started here, what's a distributed system? Well, your computer is a distributed system, right? It's just running really fast with certain kinds of synchronization primitives. And in the future, all computers will be distributed systems, all information systems will be distributed systems. why not have a really, really powerful set of capabilities inside Python for all of those use cases? I think, one of the things that gets me very excited, and it's unfortunately still not come to massive fruition in industry yet, is memory class storage. You talk about all these other pieces inside, the NVIDIA family of companies they've now acquired, but for me, the memory class storage that's coming out of Intel is incredibly powerful, incredibly exciting. And if I ever were to kind of turn into Yoda and have any saying, it would be move code to data, right? Just use the force, move code to data. Once you actually have memory class storage, you're definitely going to be moving code to data, and the data is going to sit there and be transformed. And these data ponds, whatever, these like less than enterprise data warehouse, data lake things are going to start popping up literally everywhere. And if we can get one step ahead of where the puck is going and build today distributed systems that have contemplated what federated data management looks like at small scale, that feels nice, that's still a joy to use, then I think we will structurally. You talk about ambitious. I do have ambition too, right? This is about completely redefining the paradigm of how people think about computing in a data-centric world, a cybernetic world. So
I'll say the same thing, maybe a little bit less ambitious than you. I think I'm medium ambitious, Peter. Yeah, shouldn't have poked the bear. So in Dask, actually, a lot of the really exciting features we're working on right now are around active memory management. It's around using your memory better. This is where I think Dask really shines.
That's awesome. Yeah.
Every time Dask makes a decision, it takes about a millisecond to do a little bit of thinking and figuring out, should I run this over here? Should I actually move it over here? Is right here the better place to send that code? And it turns out that there's a lot of logic you can pack into a millisecond and to figure out exactly where things should run, or to figure out, hey, I should make a replica of this data, or I've got too many replicas of this data. I want to trim it down. And a lot of the work that people have been asking us for, a really common concern is, look, I got this really big data set. I've got this modestly sized cluster because I can only want to spend $100 an hour or something on this thing. Can you do this big thing in this small space? And that's actually a really common request. And Dask does that pretty well most of the time, but not all the time. And so that's, I think, where a lot of the challenge is when you're running that race car 500 miles an hour, it comes down to memory management. That's most of what we're thinking about today. And it has huge impacts on cost reductions for usage. This is also, I think, where Dask really shines against competitors like Spark or Ray. Like Dask thinks a lot about where to send things. The scheduler inside of Dask is super sophisticated, and it's been trained by hundreds of different kinds of use cases that we get from all those different, geoscience workloads or prefect workloads or pandas workloads or scikit imaging workloads or PyTorch workloads.
Well, I mean, it sounds to me like what you need to be doing is actually building a central repository for people to submit performance-guided optimization on the scheduler back to a central repository, which we can then train with a neural net. And then you really have the Dask scheduler becoming self-aware as it tries to figure out how to optimize its own. But I mean, I think this is what I'm seeing, right? Once we have enough heterogeneity, you won't be able to, even as Dask devs, make those right heuristic calls all the time. You want performance-guided optimization for certain kinds of algorithms, certain kinds of architectures. I think that is where it's going to go.
I will disagree with that. I think we've got to make.
I'll owe you a beer if I'm wrong. If in 5 years we don't have something like that, I'll owe you a beer.
I think that machine learning models are amazing at doing lots of things, but I think that this is the kind of thing we need to make a very structured decision very quickly. And the machine learning model is probably not the right choice. I'm like thinking of when I go to Google Translate and I type in, translate something to Japanese, it takes a little while to make that translation. Like our budget is like 200 microseconds, and we're pretty, and even that has to be reduced over time. So I'm gonna pass on the machine learning model. I think this is still something where you want the clockmaker software developer finely tuning the clock to do just the right thing. But I'd be happy to.
Well, see where it goes. But I think the high level point here is that this flexibility is really an integral part of Dask's power and future-proofness, right? And it's how we kind of at a meta level make sure we're well positioned to eat future use cases. And I think that's a really powerful thing. And that's not going to be done by any single company working in the space. It really is a collective effort by lots of different folks, lots of different people working in lots of different domains pushing this stuff forward.
I've got two questions that came in through the Q&A. One's maybe for me, but I'm gonna ask it to you. Why isn't Dask as widely adopted by enterprise customers? Do you have any thoughts on that, Peter?
I'll let you take a whack at that one. Full disclosure, Rachel's one of my employees, so I feel like you should take that one. I think it is, unless it's someone else with the same name.
Yeah. So I mean, historically, I think there wasn't two things. There wasn't a clear company that you could call. You could call Anaconda, but like it wasn't Anaconda's main reason to be. So there wasn't like a clear support offering. And then secondly, deployment. Like it's actually pretty hard to deploy Dask in an enterprise setting by yourself. You kind of need to have a stack around it that handles. I'm not now getting into coiled pitch mode. I apologize, but like you need to have a product that manages, users and manages teams and manages quotas and manages security and manages auth and manages all sorts of things that take any company 6 to 12 months to build out. You could also use Coiled, which will get that done for you in a couple minutes. But it's just hard to do. And so Dask is interesting because it's been really widely adopted by individual contributors at companies. Something like 5%, according to the last PSF survey, 5% of Dask 5% of Python users, including all the web users, all the single machine users, 5% of people use Dask. So if any company with 20 Python users in it, probably someone in the company uses Dask. There's a lot of those companies.
Right.
But there isn't really top-down adoption of Dask. I think that's mostly because of a lack of a deployment product, which Coiled helps solve. The second question I'm going to give to you, Peter. So I'm going to try to paraphrase this a little bit. In the funding commercial situation, in terms of having a seat at the table, similar to what we see in the broader Python ecosystem, what about sort of more companies contributing more funds and man hours to the PSF and to C Python more generally? I'm going to add to that question, saying that infrastructural products like C Python tend not to get as much excitement as maybe sort of more top of the stack technologies like Dask or Numba or Anaconda. Do you have any thoughts on that situation?
I'm not sure I fully understand the question. Can you rephrase that? I don't know. I'm just completely missing the question somehow.
Yeah, I mean, I think how should Python be treated, or how should Python act as Python becomes more broadly adopted and plays a larger role in enterprise? How should Python change?
How should Python change?
Or how should we change around Python? How should the situation around Python change? I may be misrepresenting the question, but that's the question I'm going to ask it instead.
It's the one. Okay, I can see it here, right? So, okay, yeah, I'm having, maybe if the person who asked it could phrase that differently. I mean, the question you asked there, Matt, is that I do think there's obviously all open source, crowdsourced things in the internet. All that you might love in the internet that's crowdsourced suffers from a tragedy of the commons, right? Whether it's Wikipedia, whatever, Python. And so the situation is becoming a little better, I think, nowadays. I think some of the bigger companies are starting to step up. Obviously at Anaconda, we have a dividend program we give back to NumFocus, and we've now hired people who work on core technologies like with Piston, to make Python faster. So there's a lot of this kind of stuff. I think it's certainly better than it was like 4 years ago, but it's still not really what it should be. And I think the reason why, for instance, Apache and Linux Foundation have been far more successful than Python land is because Python is really it's really a bunch of volunteers collaborating. And same thing is true in SciPy and PyData. And only in PyData, with PyData's sudden sort of adoption in business and this opportunity, and also many of the people in PyData having an entrepreneurial bent, okay, whether it's me and Travis or Matt or Wes or whoever, we're now looking at this saying, okay, look, we know how this is going to go if we don't do something. We know how we've literally seen this rodeo before. So let's not let that happen. Let's actually put things together that can have a conversation with businesses and try to meet their needs. And I think all of us who are starting businesses in the PyData ecosystem, we have our bona fides in terms of doing community work and are sort of like what drives us, right? So that it's the community perhaps a bit more okay with that. Whereas I think in the core Python land, it is an older community that came from a time when there was a much stronger view on open source or business, and these are very different kinds of things. And then with the whole the evolution of Web 2.0 and all this stuff, it just is a different trajectory. These things come down to people and individuals as much as it is with community, as much as it comes down to community dynamics. So I do think PyData now, starting in the last couple of years, really starting to take on the mode of building new businesses. It's okay to build startups in this area. It's okay for people to build open source and have open source driven commercial activities. I think that's all really good for the ecosystem in the long run.
That's maybe a great place to end. So we're at time. I'm going to try to summarize things and say that the Spark world was actually much more effective at translating open source into business use cases. But Python and the PyData space was actually much more effective at meeting the needs and providing, like really winning over the hearts and minds of users. And that now, over the last couple of years, like Python's putting on a suit. It'll be interesting to see what happens. And the distributed computing space is a space where that suit wearing ends up being especially accelerated because of how it has to interact. And so this is really interesting interplay that we're going to see play out over the next few years as Python and the PyData space start to take over a lot more of business needs. And that'll be really interesting to watch. So Peter, I really look forward. Thank you so much for joining today.
Thank you for the opportunity. This has been great.
Look forward to collaborating with you on trying out some suits in the future.
I love wearing suits. Take care.
Thanks, everyone.
Thanks, everyone.
All right. Awesome. All right. Thanks, everybody, for joining. Hope you had an awesome time. We'll send a follow-up email with the event recording, so you can always refer back to it. Have an awesome evening.